Awesome. So yeah, I'm Jenna, and I'm going to talk today about gradual verification, which is the topic of my thesis and continued work. There's lots of things to be doing, and so I'm going to continue doing that in my professorship. But the whole crux of it is that we want to assure programs more incrementally. And so gradual verification is making improvements over the state of the art to do that. Before I get started talking about the state of the art and then how gradual verification makes improvements there, I do want to take a moment to thank my awesome co-authors and kind of acknowledge them because a lot of the work I'm presenting is my dissertation work, but as you know, dissertation work is not done just by me. It's done by a lot of other people. So I have many co-authors, undergrads, PhD students, a lot of them now PhD students, and then professors at different places, including CMU and Eric at the University of Chile. So I want to thank them and acknowledge them and their contributions to this work as well. Okay, so that's my little thanks to my co-authors. Let's go ahead and jump in. And first, we'll talk about what is the state of the art in formal verification. So I do work in horologic style, so we'll start with a little example in horologic style formal verification with Daisy, our developer, who has a simple findmax function. And she wants to make sure her findmax function returns the maximal element of a list. So she specifies the post condition here in red using the recursive Boolean functions max and contains, which denotes this fact. And she wants to make sure her code adheres to the spec. So the first thing she'll do is apply a dynamic verification tool to her spec and code. And a dynamic verifier will take that post condition and turn it into a runtime assertion. In this case, it will be at the end of the function because she has a post condition. And so right before the function returns, it will do this assertion for it'll turn these functions into runtime functions and it'll check that the return value m is the maximal element of this list. And so anytime client code calls out to findmax, it's going to have to, before returning, run this check every single time. And so what really is kind of the downside of these dynamic verifiers is that they increase runtime overhead, and you can only provide assurances on the execution paths that you can execute. So if you don't provide the right input, then we don't know that it's wrong, but we also don't know that it's right. So we don't know anything about the execution paths that you do not execute. So Daisy wants stronger guarantees than this. She wants to know that max and contains is true for every execution of findmax without any runtime overhead. So she turns to static verification instead. So if she tries to take her code and spec as is and put it into a static verifier, she's going to be sad because she's going to get a lot of errors. And they're not errors because her code is wrong necessarily or her spec is wrong necessarily. It's primarily going to be because she's missing a lot of specifications. The verifier needs a lot of help to get it to be able to provide good feedback. And this can take the form of many, many specifications, preconditions, loop invariants, fold and unfolds, lemmas. I didn't even write them out in full here, but as you can see, they're going to be a lot more complicated than her simple findmax function. And if she just wants to learn how to write these specifications, she's not going to get very good feedback along that process without providing a lot more specifications, and that's like not very good. So not very user-friendly. These static verifiers have a large upfront specification cost and cannot support incremental verification of code. So in comes gradual verification. So we want to bridge this gap by actually combining the two in a seamless way. And so the idea of gradual verification is that it can support incomplete partial specifications by soundly applying static verification where possible. And then where we can't, we have these holes in the proofs, we're going to fill them with runtime checking. So now developers can kind of pick and choose where they want to put the effort in their code in terms of full static verification. And we'll see as we do that process, the runtime checking and the flexibility of gradual verification will give much more earlier useful feedback when you're actually trying to achieve static verification along this specification process. And then maybe in other parts of your code, they're not as critical. So you just want to apply dynamic verification. So gradual verification is super nice because it allows you to do incremental verification and kind of pick and choose where you want to use different like static verification versus dynamic verification in a much more flexible way than before. So let's go ahead and see how Daisy uses a gradual verifier to build up her FindMax specifications and proofs incrementally. All right, so Daisy starts by only specifying FindMax as precondition and loop invariant as question mark, meaning she doesn't really know, but she's just gonna have an unknown specification here. And even if she's missing all those other specifications, the gradual verifier can provide verification feedback. It will try to prove what it can statically. In this case, a lot of specifications are missing, so it's mostly going to apply dynamic verification behind the scenes. But you will get verification feedback. We will not fail because specifications are missing here. And then Daisy could add more specifications incrementally, and she'll receive more static feedback from the gradual verifier. Here she's going to give a precondition, and we'll use that information to prove more things statically. And so forth, one step at a time, including one or more loop invariants, and all the way until she reaches that full static solution. But actually, she could have stopped at any point along the way when she achieved enough static assurance. So take a look at this graph, which shows the incremental buildup of a proof that a list remains acyclic after insertion. To start, Daisy uses 2 question marks, specifying only 13 lines of specification code, and this is mostly going to be proof obligations around memory safety. And even though she hasn't specified a lot, still 40% of those verification conditions can be statically verified. She can go on and spend a little bit more time, say, specifying 9 more lines of code. This will include some functional properties, maybe for acyclicness of her list, but she leaves out some helper lemmas for the proof that she doesn't want to spend time doing right now. And this still leads to 86% of her verification conditions being statically verified. And then finally, she spends that significant effort on reaching a full static solution, and that's at 44 lines of specification code. So this is not only double the lines from her previous increment, she has to write those hard lemmas as well too. So what's really nice with gradual verification is, unlike static verification, you have to reach that full 100%, really. You could stop at 86% if you find it harder to get that last 14%. So only a fraction of the work can provide Daisy most of the static assurance, and gradual verification allows you to stop there if you want to. All right, so hopefully, after all that, I've convinced you that gradual verification is a really cool idea that makes advancements over the state of the art. And so now I want to talk to you about how it works in more detail and what is the current state of the art. So I have been doing in the last year some more work, but still, like, the primary foundations that are worthwhile to talk about right now in gradual verification are the outcome of my thesis work. And so that's what we're primarily going to be talking about today. In particular, my thesis made this idea of gradual verification a reality for data structures and algorithms type programs, things like sorted list, specifically recursive data structures. So things like sorted list, FindMax list, binary search tree, acyclic graphs. And so we'll talk a lot about how that gradual verification works in that domain. A little bit more specifically about what we're going to talk about is, first, I'll walk you through how gradual verification of recursive heap data structures works at a high level. We'll highlight some key design choices while we talk about it at a high level. Then we'll do a little deeper dive. We'll talk about the theory of question mark and a little bit more about the details of runtime checking. We'll talk a little bit about the design of our tool that we implemented. So once I tell you how gradual verification should work, we did implement it. We do have a tool. And we did a performance study with that tool. So we'll talk about some interesting, because I'm sure people are most curious about what the runtime overhead looks like in the gradual setting. And then finally, we'll end with a qualitative study, taking a look at some of the interesting usage trends of gradual verification while verifying a C parser. All right, so why don't we go ahead and jump in to, well, I'm going to take a drink of water real quick, and then we'll jump in to how gradual verification works at a high level, and then we'll keep rolling. Also, I guess I didn't ask, I realized this as I was talking, I didn't ask if, like, it's okay if you guys want to interrupt and ask questions as I roll through.
Yeah, hi, Jen.
Should I keep an eye on anything?
Hi, can you hear me?
Oh, yes.
Yeah, hi. So, Jenna, the question was when so in a certain sense, it's an interactive proof that say the person who's also programming, he's he or she is able to like proof like the Daisy person that you were talking about, prove the assertions of the program being correct, right? Like, and gradually, in the sense ki initially that person doesn't know how to fill the entire what is the exact proof of the program. So there is the question mark is sort of the filler, and the stack. So your tools will be giving them enough information to like fill in the blanks with the question marks, right?
Um, yes and no. So a little bit that's getting into kind of the new work I'm doing. Gradual verification can it won't fill in the blanks for you. You still have to kind of figure that out, kind of like what you're missing, but it can provide you
Directions.
earlier, more useful feedback. Like on the runtime side, it will give you, well, I think it's more of like feedback if things go wrong, more or less. So if you wrote a wrong specification, if your code was incorrect, you'll get those errors much sooner than if you had used static verification alone. Um, and it more or less helps you write specifications because you can find out when you write wrong ones much sooner. It doesn't really like, and I guess it allows you to test specifications. So if you think you know one and you write it down, then you can get some feedback on like whether that specification is correct on especially on the runtime side. But there's no generative aspect, so we're not trying to generate missing specifications. So I think there's some abduction work that tries to do that. We don't try, you'll see it as we go along. We don't try to recreate any specifications from the runtime information or the like static analysis either.
Okay, just a follow-up question. So, in the example that we had given before, so the question mark was placed at a particular position where I think there was a pointer and then this thing. So my question is the placing of the question mark also relevant and important from the prover aspect of things?
Good question. Yes, sort of. So it is important in terms of introducing optimism into the verification system. So right now, we primarily allow question mark where you would write traditional Hoare logic specification. So you would write a loop invariant, you would write pre and post conditions,
Hmm.
we'll see predicates, you can write predicate bodies, and all of those like very traditional places where you a specification or a formula would show up. That's where question mark can also show up. Now we are thinking, because sometimes it's nice, like Daphne kind of does this a little bit with their assume versus assert. We are playing around with the idea of letting you arbitrarily introduce question mark at any point in your program with a specification. Technically, asserts we treat a search like imprecise formulas in the back end. So you could just put an assert. So we already kind of have the support for arbitrary imprecision. So just introducing a construct where you can put question mark kind of wherever in your program is something that we don't have, but I don't see a theoretical reason why you couldn't have that.
Okay, thank you so much. Yeah, you can go.
Mhm. Yeah,
You can.
great questions. Cool. If I'll go ahead and jump in because I think some more questions will be answered once I get through this next kind of section. All right, so let's talk about gradual verification at a high level and some design features, and then that'll help us to kind of do our little deep dive as well. So consider now a little simpler example that Daisy is working with. We're trying to ensure that the list remains acyclic after inserting a new node at its head. So we have our one-liner that inserts a node at the head of this list. And then we have Daisy specifies list acyclicness, and then she wants to assert that after this insertion, that still holds. And so she has to specify or what it means to be for a list to be acyclic. And so let's talk about that very briefly. She can use what's called a recursive predicate to do this. If she uses some special language constructs called accessibility predicates and a separating conjunction. So we do have, if you're familiar, a separation logic or an implicit dynamic, well, specifically implicit dynamic frames, which is a variant of separation logic. So we are utilizing a specification logic for like separation logic, if you're familiar with what that is. But I'll explain it to you if you're not. So in IDF, accessibility predicates are just these specification constructs that denote permission to a heap location. So you actually can specify heap locations in your specification language. That's the purpose. And an example of an accessibility predicate is one for root arrow value here. So we have ACK of root arrow value. And then we also have a conjunctive term that's special to this logic called a separating conjunction. And it basically acts like a logical and in a first order logic, except for it has additional semantics only for accessibility predicates, and it requires the heap locations mentioned by them to be separated in memory, so distinct from one another. So when we put everything together, basically it says recurse until you reach the end of the list. And every time you're recursing, you're generating accessibility predicates, so heap locations joined with the separating conjunction for all nodes in this list. And so in other words, acyclic of L states that all heap locations in this list are distinct from one another, which is the same thing as saying that L is acyclic. It also happens that this predicate provides permissions or ownership to all of the heap locations in this list, as well as saying that they're distinct from one another in memory. All right, so now that we have a little bit of context about the kind of static verification or specifications that we're working with, I do want to give additional context and show how a static verifier would operate on Daisy's program before then I show you how a gradual verifier would work. Okay, so if we had a static verifier, it starts out knowing what Daisy specifies, and that is the list is acyclic, but it also gets to know information when it analyzes the program. And so when it reaches the program statement where we allocate and insert a new node at the head of the list, the verifier can learn new information. So it learns that the list is no longer null or no longer empty. And it also gains ownership of the newly allocated heap locations for that new node. But it also can remember things that happened before, as long as they haven't really been changed by this program statement. And adding a new node at the list doesn't change that the rest of the list is acyclic. So we still have acyclic of L arrow next, but the rest of the list is now at L arrow next, so that's the only kind of change there. And this is great, right? Because if we take a look at what the body of acyclic of L is, when L is not null, which is the case here, all we need to know is that we have accessibility to those, the first node in the list, and then that the rest of the list is acyclic, which is what we have. So, right, we should be done. Unfortunately, static verifiers can't in general be that smart. It doesn't know that it can't assume that having the body of the predicate is the same as having the predicate itself. So you need to have, and this is an iso-recursive interpretation, just for some terminology, this is an iso-recursive interpretation of predicates that static verifiers have to adhere to. Okay, and most of them implement. So what Daisy has to do to solve this problem is she needs to provide an explicit bold statement, which then looks for the body of the predicate, asserts it, consumes it, and then returns back the predicate itself, which then can be used to justify this assert and then prove that the assert holds. So now we do see that Daisy's program is statically verified. It is correct, but she needed to add a little bit of help there for it to work. Okay, so now that we know how a static verifier proves this program correct with full specifications, we can now take a look at what happens in a gradual verifier when these specifications are missing. Okay, so what if Daisy didn't specify that her list was acyclic before insertion, but she left it question mark? She didn't know, she's not ready to write that specification, any number of things. We don't have that information that we had before. The gradual verifier can still learn things from the program statically. It still knows the list is not null because we've added something to it. It can still gain ownership of those newly allocated heap locations, and it can still retain information. It's just represented by question mark because we can't do anything. We just don't know what it was. We carry it through because we had it before, and if it was information that we could have carried through, then we want to carry it through. So question mark continues being carried through as something we've retained. Now, remember when we get to the fold, we are looking for acyclic of L's body. And when L is not null, which again is the case here, we just need to know those two accessibility predicates and that the rest of the list is acyclic. We do know the two accessibility predicates, but unfortunately this time, because Daisy didn't specify it, or or the information is missing, we don't know that the rest of the list is acyclic. So the gradual verifier can't prove statically directly this information. However, we allow it to be optimistic. It's not contradictory information to assume that the rest of the list is acyclic based on what we already know. So we let the question mark assume this information, and specifically because we don't want static verification to fail. And so what ends up happening is we get to assume that information is true so that verification can proceed normally as before to verify the assert. And so in this domain, it's a little design feature, which is kind of new. That doesn't really happen in dynamic verification, as we'll see. But in this domain, question mark can represent predicates and accessibility predicates, which is really nice for making static verification succeed. And does prove a little bit challenging and novel on the runtime side. Because, well, we've now assumed something we don't actually know is true. So it's not the only way to prove soundness then, or to ensure soundness, is to add a runtime check or try to find that information elsewhere, and we do that at the runtime. So we'll put a runtime check for that information right before we needed it, right at the fold. Okay, and just kind of a design note, because we just talked about isorecursive. At runtime, we treat predicates and we check them by turning them into recursive Boolean functions. We'll talk more about this later. But this is actually, if we treat them as our full unrolling, this is actually a different interpretation as what we took statically, and this is called equirecursive. So our gradual verification system does have to combined and make sure it works consistently, and isorecursive interpretation on the static side, and with the different interpretation we have on the runtime side, which is equirecursive. So that was a fun little challenge of dealing with predicates in a gradual setting. All right, so I think that kind of wraps up what I want to talk about at a high level. I do want to then get into the deeper dive of, so there's a lot to talk about in terms of what question mark is allowed to provide in a gradual context. So that's what we're going to jump into next. And then we'll get into more details of the runtime checking. But does anyone have any questions before I kind of switch over or do a little deeper dive? We can also just wait until after I do the deeper dive for more questions as well.
And nothing from me. Very interesting so far.
Awesome. I will go ahead and get into deeper dive, and then I'm sure I'll get lots of questions as I go along and after that. Okay, so let's talk about the theory of question mark. So remember in our verification context that we just talked about, we had, and we call these imprecise formulas. So we had any formula with question mark is considered an imprecise formula. We have some unknown information we don't know about. And we allow, what we're doing is we're allowing this imprecise formula to represent a fully precise formula with more information, specifically and in this case, specifically the information we needed for static verification to proceed successfully. Okay, and so the question is then, can we let question mark represent more things? The answer is yes. So this imprecise formula, and this is actually very convenient because this imprecise formula and other imprecise formulas might appear in different contexts. And so not every context requires the same amount of information. And so we want to come up with a semantics for imprecise formulas that can capture more representations of precise formulas. And so we actually allow imprecise formulas to represent, actually, it turns out infinitely many precise formulas, as long as they adhere to 3 conditions that we had to set. One is self-framing. So the precise formula that you produce, that an imprecise formula represents, it must be self-framed. And this is a condition of our underlying memory safety logic, which is that variant of separation logic, which is implicit dynamic frames. And just to give you kind of a rundown, I'm happy to talk more or point you to some papers on separation logic and IDF. But specifically, self-framing means if you mention a heap location in your code or in your spec, you need to have a corresponding ownership permission or an accessibility predicate in IDF to frame that permission. So if you say L arrow val is equal to 2, you need to have an accessibility predicate in that same formula to provide permission to that heap location. So that's the gist of self-framing, and so our precise formulas must be self-framed. They also should be satisfiable. And they also need to preserve the existing static information in our imprecise formula. And we'll take a look at a couple more examples and then also some examples that violate these in the next slide. And then I'll kind of explain to you why some of these conditions exist from those examples. So like we saw, and based on these conditions, it's totally okay for our imprecise formula to be in a context where it can represent a precise formula containing what we needed, which was acyclic of L or next. That's because this entire precise formula here, I'll get my pointer out. This entire precise formula is self-framed, it is satisfiable, and it is preserving the static information in our imprecise formula. But there's more precise formulas that our imprecise one can represent. It could just be the static part itself where question mark takes on true. And there is technically as many as you can create, which turns out to be infinitely many representations or instantiations of this question mark, as long as they adhere to those conditions, which, like I said, is really important because when we use it in static verification, which we'll talk about in the next slide, this allows a ton of flexibility in terms of the context in which this imprecise formula shows up in multiple places in a program. Okay, but to get a little bit more context of the restrictions here, because there are some restrictions, we are very flexible, and the point is to be as flexible as possible, but we want to put some important restrictions. Also, I forgot to note, in our theory, which is primarily in this paper, we do give a name to a function that takes an imprecise formula and produces this infinite set. It's called gamma. And really, this infinite set is the meaning of the semantic meaning of this imprecise formula. Okay. So what isn't in the set? Well, this precise formula can't be in the set. We can't let question mark take on L is equal to null because the static part already says L is not null, and that's unsatisfiable. If we let question mark create unsatisfiable formulas, it would create false, and then verification is vacuous. So you don't want question mark to be able to produce false, or you're not going to get very useful verification information because everything is just going to be vacuously true. So that's why the satisfiability restriction shows up. And then another example of what isn't in there is you can't just drop the static information, and this would break soundness because you know these things are true, and you can come up with examples then, which then lead to implications holding, where you're contradicting static information you got from the program, and so now you're in a very unsound situation. So you can't have a formula that drops any of the static information because you will end up breaking soundness. So that's why we preserve static information. And then, like I said, the self-framing one really comes from being able to make sure we can respect the ownership logic of memory safety. And so that one, you need a lot more details to explain. I won't get into those details today. Okay. Now, this definition or treatment of imprecise formulas is really important because we use it to then define implication, which is an important part of doing static verification. So now I'll show you how implication works with our new definition. So during static verification, you get proof obligations in the form of implications. Our proof obligation was we needed to prove this body of acyclic of L on the left or right here. And we needed to do so with this formula that we built up on the left, which turned out to have missing information. So we needed to define what it means to do a gradual implication. So how do you do implication when you're missing information? And that's where our gamma definition comes in. So gamma takes a precise formula only to a set of itself. And that makes sense. There's no information missing here. We don't want it to be able to represent more things because it's as precise as it possibly can be. And then we know what applying gamma to an imprecise formula is. It's an infinite set with an infinite set of specific precise formulas. And it so happens that it is okay for our imprecise formula here to contain what we're looking for in the left set. And that's important because we actually define gradual implication to be if there exists a precise formula in the left set that implies a precise formula, so we can use static verification here, implies a formula that exists in the right set, then we say that gradual implication holds. And this is adapting theory from gradual typing. And is maximally permissive without like breaking soundness and also like breaking some gradual properties we'll talk about later. So this is basically, there's other ways you could define this gradual implication, but we've chosen it to be as like this that I showed you here is as permissive as we possibly can. So static verification doesn't fail without making static verification unsound or unusable. So that was kind of the goal here. All right, so that is all I want to talk about in terms of the theory of question mark. Next, we'll switch into a deep dive of runtime checking.
So now, how do you stop the more and more precise statements from just being more and more uninteresting or like more and more vacuous? Like I'm going to fill in the hole in the statement by adding like, I don't know, false implies blah, 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 or something. Does that make sense as a question?
I think so. Well, we don't allow anything to fill in false
Okay.
because then you would just be able to prove anything.
Yeah, I guess my point is that like, I don't know, I don't fully have in my head the grammar of what's allowed to be put into a question mark as we narrow the precision of our statement, but I feel like you could potentially keep something syntactically valid and true, but by just making it vacuous and unimportant.
So I guess it's, I want to say it's, I think I might understand what you're saying. I think what the importance here is coming from those conditions. Those conditions make sure that it's not being instantiated with something that's like vacuous and true. Now, an actual implementation, so like in theory, like that should be what is making sure that we're not instantiating things that are like you then you wouldn't be able to write it. I guess this is more of a semantic interpretation, but that makes sure that you don't like syntactically instantiate question mark and carry it around with this
Yeah.
information that like is not very useful. Those conditions are really going to help with that. But in actual practice, we basically apply abduction. So we reason through the program where we don't actually, what happens is in practice, we don't actually instantiate question mark with anything explicitly that we carry around. We kind of we properly flow question mark through a program based on semantics that respect this formalism. And then when we get to a point where we hit an obligation, then that's the point at which we don't ever actually, whatever we assume at that point, we don't add it to like the fact, we don't add it to question mark to continue taking it somewhere else. We kind of just say, oh, you reached a place where it's imprecise and now you're trying to prove something with you're trying to prove something with imprecise context. And so you basically compute the diff on what you need in that implication, and then you put a runtime check there, and then you just continue, but question mark doesn't contain that information.
Okay.
So that's kind of how
I
it's
think
done
that
in
makes
practice.
sense. Yeah.
So hopefully that helps answer your question. And then one other thing that I was thinking of that I probably should mention about that. There is technically an implementation in our tool where we do carry some information that we optimistically assumed, and that is to reduce runtime checks later. That's the only case where we like actually technically instantiate question mark with anything in practice, is when we like want to save ourselves some runtime checks later. But we have to be very careful when we do instantiate to make sure that the reasoning through the rest of the program is correct with respect to imprecision and the fact that we don't know extra things. So the reasoning around what we call the optimistic heap is like very interesting and very like careful, because once you start like in practice implementation, start instantiating question mark in multiple contexts, you have to like make sure that it's consistent across those contexts. And so in most computations, we don't have to do that, which is nice. It makes our lives super easy in implementation. But when you do to try to reduce runtime checking, then it becomes a bit more complicated. Yeah. So a little bit of fun facts about some of the implementation going on there. But maybe I think what I said first definitely answers your question. But if you find the implementation stuff I'm talking about interesting, I was like, I think I had it on. I'll have it on a slide later, but our tool paper goes into a lot of detail on how we actually implement this theory of question mark in an actual tool. I think a lot of people here might find that quite a bit more interesting than the theory itself.
Cool.
But it boils down to abduction. So if you are familiar with abduction in Isel's paper, some of the biobduction work from Peter O'Hearn, a lot of those ideas go into how we implement this theory of question mark. Okay, cool. So I'm ready to dive into runtime checking if you guys are. All right, cool. So kind of in a nutshell, it's probably not that surprising what we do, but it works. So maybe it's kind of a fun because it's like what you would think is a naive solution, but it works actually. So how do we run check these formulas? Well, Boolean expressions, we just turn them into C assertions. Kind of straightforward. What's more interesting and what doesn't happen in a traditional static verification domain, or dynamic verification domain, but happens in gradual verification because we have to runtime check things that we have on the static side. We have to figure out how to check predicates. We turn those into recursive Boolean functions. And then we have to figure out how to check accessibility predicates and ownership based on the logic that our static verifier proceeds. So we have to turn this into a runtime strategy. And these are new and novel to our work. It hasn't been done before in dynamic verification. There's some new work coming out with separation logic, testing separation logic, but ours technically came out first. So I will talk to you about the strategy, specifically these strategies, because they're not things that have had to be done in dynamic verification that we know of, and is new to our work. So again, it was pretty recursive predicates are pretty straightforward. Because the specification or language we're using in the logic we're using, it's fairly run-to-one. So we just turn it into a Boolean function, ternaries into if statements. We'll return true instead of asserting true. We'll have our recursive call. But what really is the interesting part is how do we check ownership and permissions at runtime for our IDF logic. So we have this, we'll talk about what the assert act looks like, but we need this like own fields collection. And it's actually something that we newly track at runtime to be able to check these assertions. So we'll talk a lot about those. So at runtime, we have a heap and a stack that we track values in. Well, now we're also going to track the heap locations that are owned at every program point. And so we have a semantics for doing that at every program point in our imperative language. I'll show you, to give you a sense for the semantics, I'll turn to another example. So imagine here we have two empty lists. And at the start of the program, we will allocate and initialize a new own field set, and it will be empty because we don't have any heap locations. If we do allocate new heap locations, we will add them immediately to be owned. So as the moment you allocate something to the heap, we own those heap locations. And we do so here with both X and L. We will allocate and insert a new node at the head of their lists. And so all those heap locations become owned. The only other semantics we have is at method calls. That's where things get interesting as well. We haven't really been working with non-garbage collected languages, though we are going to start working. If you did have freeze and specific freeze rather than garbage collection, then what you do is we would also have a semantics that at a free, we would remove heap locations, just like we add them at allocation points. But like I said, The other interesting point is function calls. So imagine that we called out to find max for list L. And we have to, well, first we want to execute find max with own fields, but the question at method calls is what permissions do we pass from main to own fields so that we can execute correctly? And that is determined by the precondition on the function. So in this case, find max has acyclic of L, which is fully precise, and it denotes only the heap locations. So it says find max only needs the heap locations for list L, and so only those are calculated and passed to find max. The problem here, the challenge really is we're in a gradual setting. So this requires could be question mark, it could contain question mark. And so in fact, in this case, question mark might potentially denote and require for find max any location owned by main. So we have to be conservative and we have to pass everything to main. Otherwise, find max could have required it, and we might have runtime checks that might fail when we don't want them to. And so that's how we have to be conservative here and pass everything. And now find max will just execute just as normal. If it reaches different points where it has to modify the set, it'll modify the set until it reaches the end of the function. And just for the sake of this example, we'll just say the own fields we have at the end of executing find max are the same as what we started with. And so now we have to figure out what to pass back to main because find max is done, its execution finishes. We have to figure out what we pass back to main so a main can continue executing correctly. And this is, again, is just like before, is going to be dependent on the post condition. In this case, it's question mark, and we'll pass everything back to main so that it can access everything again. And so that's it. That's our simple semantics for tracking own fields at runtime. And so now we just need to check our accessibility predicates against this own field set. And that's what assert act does. So it takes the heap location from the accessibility predicate, it takes the current own fields at that program point, and it'll just look for if that heap location is in there, and then it will return true. Otherwise, it will return false. And to check the separating conjunction, if it is in there, we will remove it. All right. So that's runtime checking. And really quickly, just because it kind of ends this part of the talk, now that we know how gradual verification works at a detailed level and a high level, we can talk about some of the properties that our gradual verification technologies provably adhere to. The first one is soundness. So all specification violations, they'll be caught either statically or at runtime. Our like construction here of our verification system actually leads to what's called a conservative extension. It means if you leave all question marks out of your program and have full static specifications, you're going to get full static verification. And then we also have what's called the gradual guarantee. So if you have a subset of a correct specification, so you're missing specifications and you have question mark, but the specifications you do write are correct, you won't get any errors. And that's really important, specifically for that fact that I told you where if you're missing specifications, we don't want static verification to fail unless the specifications you do write is inconsistent with your code. So we want to be able to avoid any errors or like false positives, basically, because you're missing specifications. And this gradual guarantee is what allows us to do that, both on the static side and now we also make this guarantee on the runtime side as well. So you're not going to get failure on the runtime side just because you left specifications out. Okay. So we are at 45 minutes. So I'm keeping an eye on the time. That does end my the biggest thing I wanted to make sure I get through today, because I think that's most interesting for this audience, is how gradual verification works. The next will just be talking about and this is if you're interested about the tool paper. On the left here is our tool paper. On the right is the formalization and soundness of the paper. So the tool paper, the study, I think they're very interesting results, and I'm the two studies to talk about. But I want to leave some time for you guys if you have questions about gradual verification itself.
Hi, Jenna. I had a very basic question. So I just wanted to know how the cyclicity of the linked list is being checked finally. Okay.
At runtime or static?
No. I mean the logic of it. So what you are doing is So if the list is null, it is true. And then it has a value and a next. So whatever the accessibility thing, I'm not sure what the accessibility thing is actually doing. And then recursively, it will go on to subsequently look into other elements of the list. So if there is a circular list, where does it violate? Like there should be an and false, basically. So I just wanted to know.
So yeah, that's a great question. So you can think of it both from a static interpretation of checking it and dynamic, but I think your question is best answered with that cyclic list that you pointed out. So anytime, basically what that specification is saying, if you unrolled it, like the semantics of unrolling it, is that you're going, for every heap location, you're going to own that heap location, and it's that conjunctive term with the star. Let's see, it's probably better to go back to the actual specification since it won't take that long to get there. Oh wait, I have it right here. Okay. So pointer, here it is. Okay. So basically, semantically, this is saying every heap location is going to be unrolled and joined by the separating conjunction. And the moment you join it by the separating conjunction, this is asserting that these two are separated in memory. So when you get to a cyclic list,
Implicitly,
once you get to the cyclic part, it's
yeah.
going to fail.
Got it. I understand.
Yes. Yeah. And that's actually the echo-recursive interpretation is, I think, a little bit easier to think of, which is what I just talked through. So that's kind of what we do at runtime. So we will like basically have a set where we add like the owned fields to, or maybe we take it away to make it more performant. And the moment we try to add the same one in is when the runtime check will fail. Which would happen with a cyclic list.
Yeah. So this was a running example. So therefore, I had this question for a long time.
Oh, yeah. It's so nice that I was able to find an example that I could use for so many different like features. But yeah, it does lead to, if you're unsure about one part, then you're carrying that through so much of the talk. So I'm glad I got to answer it a little bit earlier.
Thank you so much.
Jenna, I've done this workflow, I'm sure you've done it too, where I'm in a theorem prover like talk or ASIL2, and I have some word like skip or sorry, right, in that prover that says I haven't proved this thing yet, but you can kind of take it for granted.
Like that, right? The question mark feels like the skip and sorry sort of a thing.
Yeah, that's what I'm getting at. It kind of morally feels a little bit like that. And I'm wondering if my like moral intuition lines up with some kind of fancy, Howard Curry correspondence or something, or if that's just like me being silly and not actually a real connection.
So unfortunately, I haven't worked a ton with theorem provers. I've worked mostly with Horlogic style verifiers like Daphne. So I'm not as familiar with how like the skip mechanisms work in those tools to say if there's any kind of formal connection. But there's kind of two things I've realized as we've been doing the gradual verification work that it's more of my intuition, I can't say for sure, is that it does feel like that. Like we're really trying to give you, like, whatever you reach a proof obligation and it can't be proved, there's a hole here. We don't want to fail if it's not necessary to fail. So it is, so morally it probably is like close to that skip. And I kind of think about this, I was thinking about this with the Daphne assume assert as well, which is where you can kind of pick to like runtime check something and assume it, and I don't know which one's which versus checking it. And I think it's kind of like very morally the same. It might even be there's some formal connection as well to that. We just do it more gracefully or like more systematically is what how I would describe it. Is we are systematically treating like flowing question mark through and this imprecision through. So you don't actually have to mark these holes yourself. It just automatically taken care of for you. So that's again, I don't know about skip, but if it's anything close to Daphne insert, that's how assume assert, then that's how we kind of relate to that. It's more of a like smooth, systematic transition of like skipping over things you don't know.
Yeah, that's interesting. The only tool I've used that looks like what you've been showing in these slides is Ivy. I don't know if you used Ivy before, but it's a
I've
lot of
heard of
loop
it. I haven't used
invariants.
it.
Okay,
Okay.
it's from Ken McMillan. But my experience with Ivy was that I really had to have a very strong map in my head of what my proof was going to look like in order to come up with the right loop invariants to like get where I wanted to go. And I often felt frustrated because I'm accustomed to a theorem prover where I can see the proof object and like the state of the proof currently, and then I can figure out exactly what I need to do next. But in the SMT context, it's not really like that. Like I don't get to see like the list of things above the line that are true and the things below the line that need to be made true. And so I would just feel very lost. And I feel like something that is appealing about what you're presenting is that you can kind of describe like the shape of what you want to prove, but with these holes in it. And that feels morally more similar to like kind of that stateful interaction that you have with a theorem prover. But I think I'd have to actually try it to really know if it does ergonomically feel the same.
Yeah, so I'm going to confirm what you're speculating because as I've been using the technology more and more, as it's like a lot of it, I've kind of been thinking of a theoretical perspective, but since we've been
Yeah.
implementing the tool and actually using it, it really feels like we're trying to bring interactiveness to core logic style like automatic
Cool.
verifiers, which kind of need that help, right? What
Yeah.
we don't have yet is I think there's a lot of so I mean we basically are able to get around because like one of their problems also is uh, the way that they're implemented, the moment you hit an error, you can't get around it. It assumes like you might have other errors later in the program, things are missing, but it subsumes everything. So you have to immediately deal with what's missing there and how to fix that error before then you find out others. So gradual verification kind of like gets you around that, and it really allows you to pick and choose kind of where you want to like put your effort into like fixing or adding more specifications and also like you can, I guess, static verifiers do this with like some visuals, like visuals of their execution process to kind of expose the interactive process. But I really think the dynamic checking combination and the smooth like fixing of holes will make it a lot easier with visualizations to provide more interactive and useful feedback in that interactive verification process. So that's kind of my intuition about like actually using the tool kind of like arises at. It really feels like because we aren't able to fully automatically verify code yet statically, like we're gonna need to bring some interactiveness to these kind of provers.
Yeah, that makes a lot of sense.
Cool.
Yeah, Remy, it was Ivy to your question. Um, Jenna, I think we're just about at time, but I guess like people watching this after the fact may be interested in trying your tool. They also might be interested in finding out like if you're accepting students in a lab in the future and
Right.
that sort
Good
of
question.
thing. How do people reach out to you if they want to chat? Yeah, what should the general audience of like computer science curious, let's say, 20 somethings watching this on YouTube know about you and your research program?
Okay, yeah. So great. I am sorry. I guess I was hoping that we would get through and we did get through the core of like how gradual verification works. There's tons of really cool like how we design the tool, how we actually use the tool and have some cool like user like results. That I didn't get to, which is sad, but it's all in my dissertation. Which will I be able to share my slides?
Oh, yeah, anything you want to share, whether it's links to papers, slides, whatever, just email them to me and I'll include them underneath your talk title on the website, and then people can find them that way.
Perfect. Yeah. Because I was like, there's a lot of cool results that we have. I think like for this audience, I like primarily wanted to focus on talking about how gradual verification works, but I did include slides and polish them up so that in case if anyone's interested in like the performance results or the user trends that we found, those are primarily from my dissertation, but also we have papers related to them and I can share all that information. Cool. So that kind of wraps up the research part. I do want to take a look. So what are we doing now? So that was my dissertation work. So what are we doing now at Purdue? I think this slide assumes that, and then I kind of have like a summary of my lab. So there's lots to do. We have this like it was a tool. We got to use it on some real programs, but it really only works for recursive data structures. So we have a lot of technical things to do in gradual verification to get it to work for like even more real code. And we're thinking about targeting C. So to get to C, there's a lot of really interesting questions on how do you gradualize fractional permissions, quantification, and specifications. There's tons of optimizations we need to do both on the static and dynamic side. We don't support arrays very well because we don't have quantification. So there's a ton of interesting technical questions in gradual verification that still exist that we're working on. And then it's about how do we utilize the flexibility of gradual verification to build the best verification environment that we can. So the dynamic side can be helped with property-based testing so that we can get more test coverage. So how do we integrate that with gradual verification? How do we create visualizations of the static and dynamic and their integration with like in a gradual setting so that we can teach people verification more easily or gradual verification more easily? And how can we use this flexibility for education via visualizations? And then finally, like I said, specification generation and repair. We think now that we have a more flexible verification tool, especially in that way we kind of talked about, Max, it may be more amenable to specification generation and repair, specifically with LLMs and AI, which work better in a more incremental setting. So, or in a like scoped down setting where they have, rather than having like to generate whole programs, maybe can generate like one little piece of the specification at a time, and gradual verification can kind of help with that. So that's kind of all the cool new directions my lab is pursuing. And that spans theory, tool building, user studies. I am hoping to keep hiring students. I will have to unfortunately say that it is a tricky time right now. So I can't, normally I would say, yes, I'm hiring students, but right now it's more of like, yes, maybe. So I apply, I guess, if you're interested in for next cycle. And then hopefully by then I have some grants under submission, so fingers crossed. So I'll say yes. Okay, I'm going a little off track, but yes, hiring students, go ahead and apply. Yeah, we need lots of help working on both the AI and generation. There's also interesting symbolic specification generation techniques, a lot of interesting stuff on the verification side and educational side if people are interested in user studies. Oh, this is a link to my website. So more information about what I'm looking for in the students that I hire and like other interesting projects that I'm thinking of with the gradual verification setting. More details can be found on my website, which is here.
Awesome. Jenna, thank you so much. We really appreciate your time. And if you ever want to come back and do a follow-up talk about implementation details or user studies or whatever, I think we'd love that. I personally am very biased to be pro user studies and formal methods in programming languages. I think it's like a domain where that's very important and underdone. My friend Harry Goldstein does a lot of this work that I think is super cool around
Yes. Okay.
yeah. User study stuff like that Jane Street paper, I think is absolutely wonderful. So yeah, really appreciate your time and we'd absolutely love to have you back anytime you want to talk more about this stuff.
Yeah, awesome. Thank you for having me. It was great. And yeah, I would love to come talk about more stuff. I think right now, user studies, we haven't really done any yet, but I would love to talk about them when we do.
Awesome.
Some of the case study results, yeah, I think they're the tool, I think I could definitely come back and talk for now. We have some cool feature additions that are coming soon, so would love to come talk about them sometime.
Awesome. That sounds terrific. Okay. Thanks, Jenna. And thanks everyone for coming.
Awesome. Thank you.
Adios.